Hey, in this video we'll be talking a little bit about vector multiplication, and specifically we'll be talking about the vector dot product. It's also sometimes known as the scalar product because the result is a scalar. It's just a number. You take two vectors, you multiply them together in this special way, and you get a number. And we need to know what that number means to be able to make this useful. So I'm in Visual Studio. I'm also in the Unity environment, so I have access to what Unity can provide for us. So I'll show you what it does as well. So the vector, the dot product, is a rather simple calculation. It's going to take two vectors. So let me make a vector 3. I'll call it A. Just give it some arbitrary numbers in here, and then another vector 3b. Alright, sure. So the dot product is a combination of these two vectors. It's a product, so that means it's a multiplication, and but it's a special way. So we have multiple ways we could possibly multiply vectors. So this one, you can do it in Unity using, let's see, I want a result. This is the dot result, I'll call it. And using the vector 3 class, there is a dot function. And it takes two vectors, the left-hand side and the right-hand side. And it will return a float right there. So the way you could calculate this yourself, if you don't have access to this function, or if you want to write it out yourself, if you want to modify it in some way, or if you want to do the calculation by hand, is instead writing it out. It would look like a dot x times b dot x plus a dot y times b dot y plus a dot z times b dot z. And you can go on for however many different dimensions you have. You can see that the different dimensions, the components, are just paired together, multiplied, and then added to each of the other dimensions results here to form the dot product. There's an alternative calculation too that's equivalent. So I could also say, well, if I were writing it in math notation, it would look like the magnitude of A times the magnitude of B times the cosine of, oops, let's get rid of that, the cosine of the angle between them, whatever that angle is. I'm going to just call it theta for now. This stuff doesn't carry any meaning in programming. We have to write it a different way. And but algebraically, we could use this to solve for the angle between two vectors. We could calculate the dot product the normal way with components, component-wise dot product, and we could find the dot product using trigonometry here, and we can use algebra to solve for theta and get that angle. Pretty useful. These two, the A and the B in vertical bars, each of these is the magnitude or the length of that vector. So if I were to write this out the way that Unity does it, these would be the magnitude times B dot magnitude. There we go. And there we go. So I still don't have a theta value, but whatever. If I did have the angle between them, then I could calculate this this dot product. All right. So now this is an interesting math tool because it kind of represents a product between two vectors. You're multiplying two vectors, and you're getting a numerical answer that's related to the product of those lengths. So you can see the A dot magnitude and the B dot magnitude multiplied together, but then they're modulated or scaled by some factor. cosine has a range between -1 and +1. So your maximum value is going to be this, the product between these two magnitudes. And you're going to be diminishing that product based on how aligned these two vectors are. The closer they are, the closer the angle between them is to 0, then the more of this effect you're going to have. And the farther apart they are, the less it's going to be, roughly. When they're perpendicular, you're actually going to end up with 0. And when they're in opposite directions, you'll end up with a negative value. So it's interesting to think about that between two vectors, just any two vectors. But specifically, when you work with a unit vector, let's say you have two unit vectors, you can talk about this as how aligned they are. So if these were unit vectors, let me do a dot normalize and b dot normalize. So now the dot product, let's go back to this actual calculation. The dot product is going to give us a result that is somewhere between -1 and +1. If you remember using this definition, the magnitudes are both going to be 1 because these are unit vectors now, and cosine is going to make this between -1 and +1. So the cool thing here is that the dot product between unit vectors is going to be 1 if they're aligned, 0 if they're perpendicular, and -1 if they are anti-aligned, opposite directions. So that is a pretty powerful tool. It gives us this math tool, a really quick calculation, relatively speaking, to say that one vector is, or these two vectors are pointing in the same direction, or pointing in opposite directions, or somewhere in between. Can give us some idea of how related these directions are. And then it goes even further when you have just one unit vector and one other vector, any arbitrary vector. You can think of it as a projection. It's like saying how much of this vector is in this direction, and you can get an amount. It's sort of like a magnitude that is along that direction. And then you can use that magnitude, you can multiply it by that unit vector later if you wanted to get a vector that carries information about how much was in that direction. It's pretty cool. So there's some applications. One quick one, if you're thinking about the dot product between unit vectors, you can be talking about backstab in games. This mechanic can be implemented using dot product, saying like, hey, here's the forward vector of this character and the forward vector of this other character. Let me just dot those vectors together and I can tell if we're facing the same direction. If I attack and hit you and I'm facing the same direction as you, maybe that means that I'm behind you. Another application is, say, in a racing game, you have like a boost pad on the ground. That boost is going to give you, the pad's going to give you a boost only if you're moving, that is, you have a velocity vector, in the direction that the boost pad is pointing. And so the boost pad might have its own boost force vector, and you can dot those two vectors to give you some information about that situation so that you can achieve what effect you're going for. All right, well, that's the dot product. I recommend that you try out a few calculations by hand. Try using this calculation and just throw together some arbitrary numbers just to get a feel for what this actually does. It also helps to do this in 2 dimensions and 3 dimensions and plot the results. Plot out the 2 input vectors and plot out the result, the number on one of these axes, or just think about the length of it. and it'll give you a lot of intuitive understanding of what's going on. I'll see you in the next video for some more vector math.